Welcome to Module 1, AI System Design and Architecture. Let's build something that actually scales.
Hello, my dear friends and leaders. Welcome to Module 1 of the AI System Design and Architecture Executive Curriculum. I am Manish Kumar, Director of AI and Digital Transformation. I have spent 25 years leading enterprise AI and engineering teams, and I have seen good leaders get blindsided by the same thing again and again. Not because of a bad model choice, but an architecture decision nobody flagged in time. This module exists to close that gap. We will walk through the five-layer reference architecture, the tools, and the real hands-off between them that every system in this series builds on. It's not theory, it's the same architecture that took a real program from a few hundred pilot patients to tens of thousands without breaking. Now, what's inside this module? Here's exactly what we are covering today. We will start with the problem statement. Why architecture stopped being engineer's job the moment you became accountable for it. Then a real world example, a healthcare pilot that worked perfectly at 300 patients and broke at 40,000. We will keep coming back to it. From there, requirements. The four things you need to nail down before any system design conversation even starts. Then we get hands on in system design, walking the exact five-layer reference architecture, tool by tool, handoff by handoff. Lastly, we will take that design and turn it into an actual rollout plan, architecting the AI transformation system. Now, without further delay, let's get into it. Now, let's start with problem statement. Okay. 3 out of 4 CIOs will admit, usually off the record, that they regret a major AI decision from last 18 months. Not the model, the architecture around it. The part nobody put on a slide because nobody thought it was theirs to own. So here's a quick gut check. No notes, okay? No Google. Could you sketch your own company's AI system on a napkin right now? Just take, just do it in 5 boxes, take 10 minutes of your time, and be honest with yourself. Most directors can't. And if that stings a little, good. That's exactly the room this module is speaking to. And for most of their career, that's been fine. Architecture was engineer's job. Here's the problem. At director level and above, architecture stops being a technical detail and becomes a business decision you are accountable for. Whether you understand it or not, when an AI system fails in production, when a compliance audit finds a gap, when a board asks why the AI budget doubled, that conversation lands on you, not on the engineer who wrote the code. This module is about closing that gap. Not so you can build the system yourself. So you can own the trade offs that determine whether it succeeds before they became a headline. Okay, I asked at the start whether you could sketch this on a piece of napkin or not. If the honest answer was no, you are not behind. You are normal. By the end of this module, you will be able to do that. Now, what are the key takeaways from this problem statement, right? So, we need to understand that architecture isn't an engineer's job to explain to you. It's your job to own whether or not you drew it. Moving on to next section. Let's start with a real world example. Now, picture a healthcare organization piloting a remote patient monitoring program. In the pilot, a few hundred patients, everything works fine. The variable sends vitals, the model flags the risk, a clinician reviews it. Simple. Now, scale that to 40,000 patients. It breaks. Not because of the model which got worse on the way, The model is still the same. It breaks because nobody made an explicit decision about where inference happens. In the cloud, where it's easier to govern and audit but adds latency, or at the edge, closer to the device, where it's faster but much harder to monitor and control. That one unmade decision, cloud versus edge inference, quietly determines your cost structure, your compliance exposure, and whether a life critical alert arrives in 2 seconds or 20. Nobody put it on slide. Nobody brought it to the board. And that's exactly the kind of decision this module trains you to see coming. Now hold on to that thought for a moment. In the coming section, we are going to open this exact decision up and walk through it tool by tool, handoff by handoff, so it stops being an abstraction. And the key takeaways in this particular section is the model doesn't break at scale. The unmade decision does. Now, let's move on to our next section, that is requirements. Before any system design conversation, an executive needs to be able to state four things clearly. This is the same discipline a system design interview would demand of an engineer. You are doing the executive version of it. Functional requirements. What must the system do? The very first thing the system should do is ingest the real-time vitals data from patients' wearable devices like heart rate monitoring, SpO2, temperature, and blood pressure monitoring devices. So it should send all these stats to the system, right? Then run a predictive model that flags patients' deterioration risk. Surface that particular flag to a clinicians in a form that they can act on within a defined time window. In the real program, this meant a flag had to reach a named nurse's handheld device, not just a dashboard nobody was watching. Secondly, non-functional requirements. What must the system guarantee? The first thing that systems should guarantee is latency. How fast must a deterioration alert reach a clinician? Seconds or minutes? Scale. 300 pilot patients. Today, what does the architecture need to support in 18 months? For example, for 40,000 patients, right? Availability. What happens if the system goes down for an hour? Who is exposed and how badly? 300 patients on a laptop grade database is a pilot. 40,000 patients on that same database is a lawsuit waiting for a bad morning. Third requirement, constraints. What limits the design space? Regulatory. HIPAA, Health Insurance Portability and Accountability Act. GDPR, General Data Protection Regulations. And in an XYZ health network context, the XYZ Data Security and Protection Toolkit, right? Then the next constraint would be budget. What's actually been approved, not what's ideal. Existing infrastructure, what cloud data and security investments already exist that this must integrate with. The best architecture on paper is worthless if it assumes a cloud contract your procurement team hasn't signed yet. Fourth requirement, stakeholders. Who has to sign off and what do they each care about? So the first stakeholder would be clinicians. What they need to sign off is trust, alert fatigue, clinical judgment tracked via human AI agreement rate and override frequency. Right? Then the compliance and legal team. They'll be responsible for auditability, data residency, breach liability. Then your finance stakeholders, right? Who will be responsible for controlling the cost per patient monitored, infrastructure spent, right? Then finally, you have patients. They are also your stakeholders. So for them, we need to make sure that our system is guaranteeing safety and privacy. to our patients. So, four stakeholders, four different definitions of success. Your job isn't to pick one, it's to design something that survives contact with all four at once. Keep these four in your head. Every tool we name in the coming section exists because of one of them. Now, let's move on to our next section, that is system design. Now we design the system at a level a director needs, not at a level an engineer needs. So basically, we'll have five layers every time we do a system design. First, data layer. What sits in the data layer is data pipelines, ingestion, storage, and the classification of what's sensitive. That is your PII and PHI versus what isn't. Then second, model layer. The predictive model itself, what it does, how it's trained, and how its accuracy is measured. We will have orchestration and servicing layer. How the model is called, monitored, and served in production. This is where the cloud versus edge decision lives. Then we will have governance layer, where audit loggings happens, access control happens, human in the loop overrides, how you prove after the fact what the system did and why. Human and organizational layer. Who trust this system? Who was trained on it? And who has the authority to override it? For our example, the deterioration risk uh, model needs to reach a clinician within a tight, defined safety window, which pulls the design towards cloud centralized inference, where audit logging and governance are easier to enforce. Even though it costs a little more latency than edge inference, that's the trade off we made in the real XYZ program. Okay. So XYZ is the name of a healthcare program that we have been working on, right? Now picture the opposite choice made badly. A health system picks edge inference just for speed. Nobody asks about the audit trail. 6 months later, a regulator asks one simple question: show me exactly why this patient's alert fired. Nobody can answer. That's not a technology failure. That's an architecture decision nobody made on purpose. And now it's a compliance crisis. We have named the five layers. Now let's walk through them the way an architect actually would. Not just what each layer is, but how one single piece of data moves through all five, step by step, tool by tool, until it turns into a decision a clinician can act on. First, the source. It all starts with the patient, their wearable devices, captures heart rate, oxygen level, temperature, and blood pressure all day continuously. And in a real virtual ward program, this isn't one single gadget. It's a small kit of clinically validated devices, a single LED ECG monitor like the uh, Alive Core, Cardia, Bluetooth blood pressure cuff like the Fora P30, and a pulse oximeter from a brand like Nonin or Choice Med. None of these are consumer smartwatches. They are purpose built, often FDA cleared devices. Because a remote monitoring program you can defend in front of a regulator can't run on a device that isn't FDA approved. And this isn't a file that uploads once a day. It's a live stream, one small reading every few seconds for every devices on every patient. Now multiply that by 40,000 patients, each wearing three devices. That's a real high throughput problem, and no AI model has even run yet. Here's how that connection actually works. Each device pairs with a gateway over Bluetooth Low Energy using something called the Bluetooth GATT, Health Device Profile. That gateway is either a small hub or an app on the patient's phone. It collects every device's stream and sends it on over cellular or Wi-Fi to a cloud IoT endpoint, like for example, like AWS IoT core or Azure IoT hub using a protocol called MQTT. That's the real first hop, and it happens before any of this even reaches Kafka. That's the whole handshake, start to finish, so that next time someone in a vendor pitch says our device supports BLE and MQTT, you will know exactly what conversation is actually happening underneath those words. Let's move on to data layer ingestion. Now that stream has crossed into the cloud through the IoT endpoint we just walked through, from there, those same readings land on a streaming platform, something like Kafka, Confluent Cloud, or Red Panda. Think of it as a loading dock. The moment a reading arrives, it's written onto a queue in order, safely stored, ready for whatever needs it next. And this is also where we tag the data as PII or PHI right at the door before it goes anywhere else. Compliance built in from day one and not bolted on later. Technically, here's what's happening. The gateway's MQTT stream lands on the IoT endpoint, then a connector, something like Kafka Connect or AWS IoT Core, built-in Kafka rule, bridges it into Kafka. That bridge is the real handoff. It's the moment the device world meets the data world at one single connection point. Now, let's move on to data layer stream processing. Next, a tool like Apache Flink or Spark Streaming picks up right where Kafka left off. It does the real time cleaning work, smoothing out noisy readings, calculating rolling averages, and flagging anything out of range. This is the step where raw vitals turn into a signal we actually use. Flink reads straight from Kafka topic using its own built-in connector. It's a constant ordered read, not a check-in every few seconds kind of pattern. That's exactly why it can process a reading within milliseconds of it arriving instead of on a delay. Now, let's move on to data layer feature store. That cleaned up signal from Flink then lands in what's called a feature store. Tools like Feast or Tecton. It serves two different jobs at once. Data scientists use it offline to train future models, and the live production model uses it too for instant lookups right now. That live lookup runs through something lightning fast like Redis. Because if a feature store takes 3 seconds to answer, the whole point of a deterioration alert is already lost. The feature store actually offers two separate doors in. One is a batch API for offline training the model. The other is a fast, low latency online API, usually gRPC or REST, for live production lookups. And the model only ever knocks on that second door. Same data underneath, but two completely different ways of getting to it. Here's something most executives never actually get explained to them. The model doesn't sit there watching the data stream. It calls the feature store on demand. That's a lookup, not a subscription. Every time a new reading changes a patient's risk profile, one request fires. Give me this patient's latest numbers. That's the moment the data layer hands off to the model layer, not a file being processed along, but a live call happening in the real time. Now let's move on to model layer. That lookup request is what wakes the model layer up. The model itself is tracked in ML flow and served through something like SageMaker or Azure ML endpoint, sometimes coordinated through Kubeflow. And it scores that patient's deterioration risk is milliseconds. MLflow keeps a record of every version of that model that's ever gone into production. So if accuracy starts to slip 6 months from now, you can trace it back exactly which version, exactly which training data caused it. That model serving endpoint is really just a REST or gRPC API. Both SageMaker and Azure ML work this way natively. So calling the model is technically no different than calling any other web API. You can send a request and you get back a JSON response with the prediction. Here's an important distinction. The model doesn't get to decide how its own answer reaches a human. That decision belongs to the orchestration layer, an inference gateway built on something like Data IQ or Stack AI. Every single prediction has to pass through this one checkpoint, and this is exactly what makes the cloud versus edge decision real. Because inference runs centrally in the cloud, this gateway can log it, rate limit it, and audit every call before it goes anywhere else. Now let's move on to orchestration, that is serving layer. That's the same gateway we just talked about. In bigger, more complex deployments, it also acts as a model router deciding which model handles which type of request. But in our case, its main job is simpler. It enforces that one governance choke point we just talked about. Technically, the gateway is a REST API layer that sits in front of the model. It adds authentication, logging, and rate limiting before a request ever touches the model. In plain terms, it's a reverse proxy with a memory. Once a prediction clears the gateway, it gets written straight to an audit log in real time. Using something like Data IQ Govern, this happens the moment it occurs, not after the fact. And that's exactly what lets answers a regulator's questions 6 months later with here's the exact record. Instead of we think it happened this way. Let's move on to the governance layer. That audit log we just talked about lives right here in the governance layer. And the access control lives here too. Who's allowed to see this alert? Who's allowed to override it? And every single override gets a permanent record with the clinician's name attached. Those audit logs get written as structured JSON events into their own dedicated logging pipeline, completely separate from the main application's data path. That separation really matters. A failure in the compliance system can never take down the clinical system and the other way around. And finally, the alert reaches a named clinician's devices, not a dashboard nobody's watching, a real person on a real device. And this is where the system starts reporting on itself. A tool like Confidence AI tracks whether the clinician agreed with the AI or overrode it. That's your human AI agreement rate. KLAS are collaborative surveys check from time to time whether clinicians actually trust the system, and Power BI or Tableau rolls all of that into the same board level report you learned to read at the start of this module. That final alert usually travels over standard mobile protocol, APNs for iPhone, FCM for Android, or on a hospital workstation, it writes an FHIR subscription alert, which fires the instant a matching record gets written. It's the exact same pattern your phone uses for a text message, just repurposed here for a deterioration alert. That's the whole journey, device to clinician and back to your boardroom dashboard. Every single arrow in figure is a real handoff between real tools with a real name. And once you can walk that loop the way we just did, you have stopped being a director who simply sign off on architecture. You have become one who actually owns it. Now, let's move on to our next section, that is architecting the AI transformation system. We have designed the system. Now, let's talk about how you actually roll it out. A system design is not the same thing as a transformation plan. The last step is turning that design into how your organization actually moves. And this is the part most technically strong leaders skip. That's exactly why they stall out at director level instead of reaching VP. Ownership. Name one single executive owner for this architecture, not a committee. One accountable name. This is the person who would have to explain a Kafka backlog or a gap in the governance log to the board. So it should be someone who actually understood the walkthrough we just did. Shadow mode. Run real production traffic through the exact pipeline we just walked. Kafka fling the feature stores the model on a small group of patients, but run it silently. Log every predictions without acting on it. That way, you catch problems in the loop before a single alert ever reaches a real clinician. Governance gate. This is where the audit trail from Data IQ Govern and the Clinical Governance Board sit down together with the real shadow mode output. Before anyone flips the switch to life, treat this as a hard stop, not a formality. Phased rollout. Start with a limited pilot, then expand it in stages. Scale the same pipelines throughput, more Kafka partitions, more Flink parallelism, instead of redesigning it from scratch every time. Success metrics. Define what working actually means in board language. Alert latency, false negative rate, human AI agreement rate, and clinician trust score tracked through tools like KLAS, ARC Collaborative, and Confident AI. Not just the model is live. The real program never skipped the governance gate just to hit a launch date. Clinicians' training and sign off happened before the pilot expanded. And that's the entire reason adoption crossed 50% instead of stalling out like most hospital AI pilots do. This is the exact muscle we are building across all of our modules. Seeing the architecture decision before it becomes a crisis and owning it in a language your board can actually act on. Get this right once and something shifts. You stop being the person who explains what went wrong. You become the person the board trusts to say what happens next. Own the trade off before it owns you. You now know how to spot the architecture decision hiding inside every AI initiative on your desk. But architecture is only half the job. The other half is surviving the people who will try to poke holes in it. Regulators, auditors, and a board that's read too many AI horror stories. That's module 2. What changes when the system you are architecting has to survive a regulator, not just a scale test. Download the reference architecture canvas in the link below. I'll see you there in our next session.